Hey everyone, microphone check. My name is Yuri. This is Alex. We're from ATR team at Intel Security, working on the firmware over the last couple of years. The presentation today is Breaking Bad BIOS, or Attacking and Defending BIOS in 2015. First couple of things. Thank you for coming over here. I know 10 o'clock is pretty early after a party night, so thank you. Thanks Sam, Hugo, and the rest of the REcon team for inviting us. And especially thank you to Sergey brothers and Anya for actually listening us talk yesterday during the party. So that takes a lot of courage to switch the party to listening to the All right, so we are actually talking heads here today, and this is the work of the entire team. And a lot of vulnerabilities were found by the rest of the guys. A lot of vulnerabilities coordinated by the rest of the guys, and exploits developed for them. So let's start. Today's agenda is we'll primarily focus on the major classes, several, not all of them, but the major classes of vulnerabilities in the UEFI firmware and the BIOS discovered in the recent 2 years. So we will not talk about everything as we usually like to do, but we'll talk about everything in the, or almost everything in the past 2 years. We will also kind of discuss the overall state of the firmware security in the recent 2 years, including how those vulnerabilities can be detected. Some of them can be, and including how those vulnerabilities are being mitigated by the industry. So, for those of you who are fans of Soviet sci-fi or post-Soviet sci-fi, most of the quotes here are either from or based on books or novels from Strugatsky brothers. The last brother, Boris, he died 3 years ago, or 2 years ago. So I'm a fan of them. So as a start, we seem to have a little bit of a problem in this area with 37 unique vulnerabilities publicly disclosed in the last 2 years by only a handful of researchers looking at that space. And 37, as you can imagine, those are the ones that were known at the moment. And we don't know what we don't know. We don't know how many vulnerabilities are being exploited in the wild actively, how many vulnerabilities are found by nation states or some other actors. So, in fact, multiple of those vulnerabilities, of those 37 vulnerabilities, are classes of issues. They're not a single bug. They're not one buffer overflow. They're a class of multiple issues, with many instances present in multiple firmware products. For example, SMI input pointers, SMI callouts, or indiscriminate usage of UEFI variables, which is a configuration for UEFI-based firmware. Many same issues affecting multiple firmware products at once. For example, you might have heard about the S3 boot script issues, the UEFI variables, again, as issues with the SMI handlers. If there's one issue in one product, there are likely to be multiple of them, or even many of them in the same product. And I'm looking at the back of the stage because I once almost fell off the stage during talking. So, yeah, and even the basic things like missing write protections on the BIOS firmware. So, in addition, there is a reference code branch for the UEFI firmware EDK2 branch. The issues in the EDK2 branch are being discovered, and they might have found their way into the final products, who might be taking code from the reference implementation, or they may find their way into the future products as well. And as we all of us know, updating firmware is not really a trivial thing to do. So these are the issues. These are issues primarily discovered in 2013, 2014. We started looking at the vulnerabilities, basically in the context of bypassing some security technologies that are building on top of UEFI firmware, or the BIOS, like full disk encryption systems with TPM, or secure booting of the OS. So we found in multiple of those that would allow bypassing secure boot, for example, jointly with other researchers from, let's say, Legbakor and other. Then a number of vulnerabilities were found associated with the UEFI variables, including first bypassing secure boot, then essentially making system unbootable or breaking the system through the UEFI variables. Then number of vulnerabilities were found in the capsule update for some of the specific systems. A number of vulnerabilities affecting BIOS write protections, like for example the SMI suppression attack, or the speed racer, which were found by Legbakor. Then at some point in 2014, we had a good look at the open source reference implementation together with other researchers, and found a number of vulnerabilities there, including things like capsule update vulnerabilities found by Legbakor, the issue with UEFI variables where someone can bypass the boot services only protections of the UEFI variables and reinstall that variable with the runtime attributes. A number of issues related to the variables. A number of issues related to the SMI handlers, including race conditions and arbitrary SMI handler override. We'll talk about those a little bit later. Padding verification in the RSA, which is the base for the secure boot checks and other checks other signature-based checks. And 2014, 2015, so the trend continues that there are quite a few issues being found. More and more researchers start looking at that. You can see that the Discover column now has a little bit more names in it, with issues being discovered not only on PC systems but also on Macs. For example, the EFI option ROMs discovered by Trammell Hudson, and actually are based on the earlier vulnerability discovered by Jim Fear. And the recent problem with Flash being unlocked on Macs after the system resumes from sleep. So the preliminary conclusion to that is your system is definitely maybe vulnerable to the BIOS vulnerabilities. So how do we solve that problem? One way to solve that problem is like this. But we know where this ends. So maybe that is not the best way to solve this industry-wide problem. That's why we will talk about some of the classes of those issues which affect multiple products and typically have multiple instances in each product. We'll focus on 4 types of vulnerabilities. One of the recently discovered issues associated with the BIOS trying to, or when I say BIOS, it doesn't necessarily mean the BIOS in the legacy term. It may mean the existing EFI-based firmware or UEFI-based firmware. So when the BIOS is resuming from sleep state, when you put the system to sleep and then resume, then there are vulnerabilities associated with that process. And the second class of issues is the attacks through UEFI variables, which seems to be very prevalent on a lot of systems. Attacks via the so-called bad or poisonous SMI input pointers, which result into code execution in the SMM mode. And the attacks via the SMI callouts, which also result into code execution in SMM. I did I named all of those vulnerabilities. For those of you who like names, S3 sleep resume boot script, bad BIOS variable contents, SMI handler bad input pointers. You can see hashtags. Or the last one is this vuln seriously had to be gone long ago. So let's start. How many of you have sleep problems? Well, a few. Well, many more of you have sleep problems, I believe. So let's talk about those sleep problems. Attacking via the S3 resume boot script, which is sleep resume boot script. All the issues in that class are happen during system waking up from sleep. So there's a CVE for those issues. They kind of the whole type of issues. First, those Freddy Krueger vulnerabilities were independently discovered by us and researchers, other researchers, Rafal Wojciuk from Bromium and Legbakor researchers. So Rafal and Corey talked about those issues last December, and they have a white paper and a presentation on that. Then the details, the POC exploit was developed and described at length by Metro Oleksandr in this reference. And also recently Pedro Villaca, apologies if I pronounced it incorrectly, was found related vulnerability in Mac EFI firmware where flash lock is getting lost upon resuming from sleep. So, what are those problems? I'll explain a little bit more details about what resume boot script is, but first how to find it. The resume boot script can be found on some systems, especially on vulnerable systems, in a UEFI variable called ACPI global variable. It points to a structure in memory which contains another set of pointers to other structures that the UEFI-based firmware typically uses when it resumes from sleep. And one of those pointers is the pointer to the boot script itself. So you can see that pointer is exactly where this S3 resume boot script table is in memory. So that is a kind of structure defining all of those pointers in memory, including, you can see that ACPI boot script table pointer is at offset 18 hex in that structure. This structure is somewhere in memory and on vulnerable systems in unprotected memory. So this is a you can see the dump of the boot script containing the opcodes. So what is boot script exactly? Why is it called script? When EFI firmware normally boots, it executes sec security stage, PEI, pre-EFI initialization stage, then followed by Dixie stage, driver execution environment, where the bulk of code runs. Multiple binary PE COF executables are running during Dixie stage. Those are called drivers for different devices, sometimes just service drivers without specific device. A lot of code, and that code initializes system or continuous initialization of the system after memory is available after a pre-EFI initialization stage. So when you put system to sleep, you don't really want to wait all of that time when you wake up from sleep. You don't want all this code getting executed. And so the EFI-based firmware solved that problem by introducing this concept of a script, where on a normal boot, each driver, firmware driver, when I say driver, means firmware driver, not kernel mode driver. So each firmware driver records the configuration it makes to a hardware into a script-like table, creating multiple opcodes that this script will get executed by firmware upon wake up from sleep state without actually running all of those drivers, without executing all of that code. So only PEI stage and security stage, of course, is executed on resuming from sleep. Then just the initial early component of the Dixie stage, Dixie init, is loaded, which transfer execution to a S3 related component, which knows how to interpret the boot script, execute all of the opcodes from that boot script, and this process restores full configuration as it was done on a normal boot prior to sleep. without actually going through all of that code. So those are opcodes from the screenshot below, from the screenshots a couple of slides ago. There's a position of the opcode within the script. There's an opcode value. There are depending on which opcode it is, there's an address of the register. There's a value that is being written to that register. So this is how those opcodes look like. The first one you can see, it's actually the very first opcode in the boot script. It's a memory write. It's a memory write to an address FEC 5 zeros with the value 0. It's actually not a memory write, it's an MMIO write. It's writing to MMIO register, memory mapped IO. The second opcode, which is not really the second opcode, it's a 359th opcode in the script, is a IO read write. It's actually writing some value 21 to a register 430, which is a register somewhere in the PM base. But it's not just writing, it's actually reading, modifying, writing. That's why it's a read-write opcode. So, and that's why there's a mask. You can see how many opcodes are in the script. There are more than 1,000 of those on typical system. This opcode has a position of 359. So what other opcodes are present in the boot script? IO port write or read write, memory write or read write, PCI configuration registers write or read write, SMBOSS execute, so you can execute a specific instruction on SMBOSS from the boot script. Stall, when you can wait for some amount of time, the firmware will wait. The dispatch opcodes, those are interesting opcodes. They execute arbitrary code. Very useful opcodes for attackers. Information opcodes, there are more opcodes like stall opcodes that wait for a certain register to appear, certain value to appear in the certain register. A little bit more details. This is an example of IO port opcode. This opcode writes to a specific processor IO port, and the port here is the you can see address. It's port B2. For those of you who work on a kind of PC firmware stuff, you know that this port is the APMC port that is used to trigger a software SMI event. This opcode is writing value BD to this port, so it's sending an SMI. Now, the other opcode is dispatch opcode. There are two types of dispatch opcodes. In fact, some of the firmware products may have their platform-specific opcodes or firmware-specific opcodes, dispatch opcodes. So this dispatch opcodes basically executes a code at the entry point. You can see the address. It's a physical. It's a linear address, but it's identical mapping. So it's a physical address in the firmware. So it executes certain code early enough while interpreting the boot script. Now, this opcode is PCI configuration write opcode. It writes to a PCI configuration space, to a PCI configuration register of some device. This specific opcode, 569, it is writing value, you can see value to a 1 byte, to a register with an address 1F00DC. That's a offset DC in device 31. Device 31 is an LPC bridge in the chipset, and this DC offset is called BIOS control register. BIOS control register is responsible for some of the write protections of the BIOS firmware in the SPI flash, in the non-volatile memory. So writing to some specific value to that BIOS control register either enables properly all those protections of the BIOS firmware in SPI flash memory or disables them. So this specific value 2A, it's correctly enabling all of the write protections of the BIOS firmware in the SPI flash. A different value is if it's written, then it may disable protections. So what can go wrong with this architecture? First, the address to the actual boot script, or the structure, which has a pointer to the boot script, is maybe stored in a runtime accessible place, in a place accessible to the OS, and therefore OS level malware. For example, if you consider this ACPI global table variable, if it has attributes non-volatile, RT runtime, BS, not that BS, but boot services only. So in that case, this variable is accessible from to anyone executing with the OS privileges. And in fact, even more, because OSs provide API to the user mode to talk to the variables, to write the variables. So in fact, this is accessible to the user mode applications on most of the OSs. So if that address to a boot script table is stored in such a variable, then anybody can modify it and point to a different, completely bogus boot script. And when system resumes from S3, the firmware will execute completely bogus S3 boot script. Or the boot script itself may be stored in a memory accessible to the OS and the malware in the OS, so that malware could just modify that boot script table before putting system to sleep, and after a system will resume, wake up from sleep, that modified boot script will get executed. Now, remember that there's a actual code interpreting that boot script and executing the opcodes. Some implementations don't want to boot even that code. So what they do is they actually stash it to memory, put the system to sleep, and remember that in sleep, memory, contents of the memory is preserved because the RAM is in self-refresh. So all of the contents are left in memory. And when the system resumes from S3, the firmware finds that module, the boot script executor, and jumps to it. And this boot script executor already, in its turn, finding the actual table, boot script table, and interpreting the boot script table. So if that module, that executable, is stored in unprotected memory, then you don't need to modify the boot script. You just need to modify the code that is executing the boot script. Now, assume that both the code and the boot script table are protected somehow. If you remember those dispatch of codes that jump to a arbitrary code, arbitrary function to do some extra initialization of the platform, the dispatch of codes, they have the addresses of the entry points. So even if the boot script is protected, the dispatch of code points to some code. And if that code at that entry point is stored in a OS accessible memory, then that code can get modified by the malware and will get executed. And finally, certain systems or some systems may just forget on a normal boot when that firmware executes on that system. On a normal boot, they configure the hardware with, let's say, and enable BIOS protections, but they forget to store or save that information in the boot script. And if they do that, if they forget to do that, then upon resuming from sleep, that configuration will not get restored. So if on a normal boot you had some protection, like BIOS is write protected, then you put the system to sleep, wake up, and that protection is gone. And that happens because may happen because firmware just forgot to put the specific opcode restoring that protection. So what's the impact? Malware in the OS is able to change the actions that are performed by firmware on S3 resume before OS resumes at the waking vector. So what? Okay, explaining further. Malware can execute arbitrary firmware code during earlier resume, way before the OS. Malware can disable hardware protections such as BIOS write protection, which are going to be restored by the script. Malware can install persistent BIOS rootkit in the spy flash memory because the protections are not there yet. Or it can rewrite arbitrary memory or execute arbitrary code, which I already said for some reason, in the context of system firmware early enough in the PEI stage, or bypass OS security measures like secure boot, for example. Pretty bad impact, right? For those of you who are far from firmware, yes, it can also steal your PGP keys. So the nice quote that suits this vulnerability is that 93% of the days in the year start the same. The alarm clock rings, and then your vulnerable BIOS boots or awakes from sleep. Let's go through a demo. I'll explain a couple slides on the demo, and then I'll just show that on a system. So imagine that you had BIOS protected in SPI flash memory. So we're running our chipsec test that is testing the write protection of the firmware. And it says that, hey, BIOS is write protected, everything's good. You can see that the BIOS control register has value 2A, which I previously mentioned. But then, so basically you can sleep well. Go ahead and sleep well. But before you go to sleep, an exploit executes this, approximately this code. So it finds the boot script unprotected in memory, then modifies, and it finds the opcode that restores BIOS protection with the value 2A. So that opcode is restoring BIOS protection in a state on, and changing it to restore BIOS write protection in the state off. After you wake from sleep, the same test that is checking BIOS write protection says that it's not completely protected. When it says that, it's pretty much not protected at all. So let's do the trick. And I will actually, I wanted to record a demo because videos fail much rarer than the actual demo, but because we had a very intense training, I actually couldn't do that. So if you think that you'll do something during the training other than the training itself, you're mistaken. You probably won't do anything. So let's just do the live demo. So let me check protections on this system. And I know, unfortunately, that this system is not protecting the BIOS firmware on the SPI flash. I'm using it for demo specifically. So I'll do it a service. I'll enable the write protection. Okay, so now no one from the software should be able to write to the SPI flash, which I won't do. I don't want to break the system I project from. So now you can see that the write protections are, you can see past somewhere here. BIOS is write protected, so we're fine. Now I'll find a boot script that will get interpreted and executed upon resume from S3, from sleep state. You can see that we parse the boot script. There are opcodes here. I'll find the opcode that is responsible for restoring BIOS write protection. You can see this is the opcode. It is restoring a bad value. It is restoring, originally it is restoring a value that is really not enabling BIOS protection. But I'll restore a different value. Anyway, so now before going to sleep, I'll actually run a tool that will modify that boot script in memory. It will find an opcode. I'm hoping so. Yeah, it found an opcode in the boot script that is responsible for restoring. You can see original value 8. Original value 8 and modified value 9. So both of them are bad. I'm just replacing it with a little bit worse value. Oh, yeah. So now I'm just closing this thing. Hoping that it will come back again. Okay, it's up here, should be there soon. Okay, yeah, it's up. You can see that it happens a little bit fast than usual. Yeah, you wouldn't boot the system that fast. That's why it came up from sleep. Now, the only thing I will do right now is I will check the BIOS write protection. And you remember that before putting it to sleep, it was on. Now you can see that it's failed. BIOS is not protected. So the only thing I did is I closed the lid, opened it back again, and BIOS protection was gone. I did that just for demo purposes. In fact, you don't really need to ask the user to close the lid and open it back. It's just you just put the system to sleep via OS means, or just directly writing to power management registers in the chipset, and it'll wake in an amount of time that you told it to wake. Now let me dump the boot script again. And find the same opcode, and you can see that this opcode in the boot script has value 9 instead of 8 as before. So that opcode got executed, and this is the value you actually see in the this is the value that you actually see in the BIOS control register right here. It's value 9. Okay, so protections are completely gone because we've been able to exploit the S3 boot script. And this is just basically showing that the boot script, after resume from sleep, this has this value which is not properly restoring BIOS protection. So how do we detect and mitigate those issues? First of all, there's a script in chipsec currently. It's not in the open source. It's going to be an open source branch of chipsec pretty soon after REcon. So that module, you can run it on any system. You can test whether the firmware is properly protecting, has mitigations against those S3 boot script vulnerabilities. So how do we fix those problems? Well, it's those are pretty common sense recommendations to whoever develops the BIOS firmware or the platform manufacturers. Do not keep address of the boot script to the boot script, or a structure with a pointer to the boot script in unprotected variables. Do not save the boot script table itself to the unprotected memory. Or memory that is accessible to the DMA devices. There's a mechanism in the reference code implementation for REcon that is called logbox that can help with protecting the boot script. Do not save the actual executable that is interpreting the boot script in unprotected memory. And I'm saying that again in number 4, do not save the pointer to the boot script in the EFI variable. Well, I must have modified those slides in between training sessions. And of course, review the actual dispatch opcodes or the entry points to those dispatch opcodes such that they do not point to a code, they do not jump to a code which is in unprotected memory. So one of the ways to protect the stuff in EDK-based, in EDK2-based firmware, in EFI-based firmware, is a so-called logbox. So on the left, you can see a boot script plus some management structure pointing to that boot script. On a vulnerable system that is red, that is outside of protected memory. In fact, you can use logbox as a generic mechanism. You can protect arbitrary data using arbitrary mechanism. You can use read-only variables. You can use some encrypted storage or something like that. But this example specifically shows using SMRAM to protect boot script. So remember that SMRAM is not accessible to regular malware, minus vulnerabilities in the SMI handlers, of course. But so basically, this EFI-based firmware systems, they may place that boot script and the executable that will be interpreting the boot script into a protected SMRAM memory, and execute it upon resume off the SMRAM without going out into the DRAM. So there's a link to a actual open source implementation of this mechanism in EDK2. Here's one example how the reference implementation saves the actual boot script to the SMRAM, and then it sets a flag that says that, hey, upon resume, execute that in place without copying it back to DRAM, without executing from unprotected memory. With that, let me jump to another class of issues related to UEFI variables. UEFI variables is the main mechanism to store configuration, including non-persistent configuration for UEFI-based firmware. So what does firmware actually stores? Which settings it's storing? First of all, it uses the variables, UEFI variables. Some of those variables are non-volatile. They're actually being stored together with the BIOS, with firmware on the SPI flash memory on non-volatile RAM. Variables can be boot services only accessible or runtime accessible. Boot services accessible variables accessible only to the firmware or the firmware drivers before the OS. Typically, somewhere at the end of the bootloader, those variables stop being accessible to the software. Or the runtime accessible variables, those are accessible to pretty much any code in the OS until the reboot, starting from reboot, and until the next reboot. The typical way in modern UEFI-based systems to access those variables are through the SMI handlers at runtime. And also, the interesting fact is that most OSs, they do expose API to modify those variables, but not all, but only runtime variables. So, for example, you can see that the set firmware environment variable on Windows, or the FIVAR as far as devices on Linux systems. Now, firmware actually stores a lot of settings. This is the dump of parts of those settings in the UEFI variables stored in some system. It was done using chipsec as well. So you can see a whole bunch of those variables and settings stored in those variables. One example is ACPI global variable that we saw already, storing pointer to the boot script table. Another variable is a boot order. It's the variable that you use when you choose the boot order, where to boot from in the BIOS setup screen. That's the variable that actually stores that boot order. The secure boot certificates, the root certificate, platform key, other certificates, whitelist, DB, blacklist, DBX, those are also variables. They're stored in variables. Or the setup variable, which we'll talk a little bit later. So the setup variable is the variable that is storing all the settings you choose in the BIOS setup screen or the UEFI setup screen when you boot the system. Now, what we have found, or the things we've found stored in the variables, and unprotected variables, read user mode accessible variables. Secure boot configuration. We've talked about that in one of the presentations we gave at CancerQuest last year. The addresses to structures or buffers in memory, which firmware, when it boots, reads from or writes to. The policies for hardware configuration or protections, including hardware log bits, such as the BIOS write protection policy, or flash lock, or BIOS interface lock. The policies disabling or enabling security features, depending on what you like more. Or the data which firmware really needs to just boot. There's data stored in non-persistent configuration that just is needed to boot the system. Or the secrets, sometimes even BIOS passwords. Who cares about them anymore? But BIOS passwords are sometimes stored in clear in those variables. This obviously cannot be good. So overwrite early firmware code data if there is an address stored in the variable. If there is an address stored in the variable and the firmware reads it and then writes to that address, then anyone user mode can modify that address to point to the firmware code or data itself. And so the firmware upon early boot will write to that address, overwriting its own code or data. Or bypass UEFI secure boot OS secure boot if secure boot configuration is critical settings or even keys stored in those unprotected variables. Or bypass or disable hardware protections like BIOS write protection if the policy for that BIOS write protection is stored in the variable. Or just make system unbootable or brick the system if the data is stored in the variable that is required for system to boot and malware just corrupts it. So, but that was a theory. In practice, there were found multiple unique vulnerabilities, approximately 50 different instances of vulnerabilities in different systems and in reference implementation related to UEFI variables, only recently. Both the open source reference code as well as actual implementations, UEFI-based implementations, suffer from those issues, which results into a OS secure boot bypass, unbootable platform because of the corrupted contents of the variable, buffer overflows when consuming the variable contents, arbitrary overrides because of the pointers stored in the variable, bypassing boot services protection by reinstalling the same variable with lesser protection attributes, with the runtime attributes, or bypassing physical presence, user presence of some of the variables. So, one example of such vulnerabilities were discovered by Legbocore and us is related to setup variable, and it has a VU number. You can look it up later. So, who needs setup anyway? Setup. Already we've showed that setup, some systems stored secure boot configuration in the setup variable, and that allowed us to bypass secure boot on those systems. Now, user mode malware can access this setup variable and can just write garbage in it or just delete it. In addition, if there is a default contents that is being restored by the firmware when setup is not available, some systems may store that default also in the unprotected variable, for example, std default, so the attacker may delete it or corrupt it as well. So when this happens, then the system may never boot again because it really needs those settings, and they're been corrupted. I won't be making this demo on this laptop, but why bother about this? Just bring it to the IT service desk and ask to reinstall your firmware on the laptop, like we normally do, right? My Outlook doesn't open, or my Windows doesn't boot, so my system doesn't boot. Can you reinstall the firmware? So that's probably the reaction you'll get from the IT service, right? So you might have just bring this thing to them to get the same reaction. It's not easy to do. So how do we avoid problems associated with the variables? Again, well, first, keep calm and secure them. It's not a rocket science to secure configuration. There are certain just common sense recommendations how the firmware has to handle those variables. First of all, limit the access to the variables. Separate critical settings from non-critical, from other settings. Store them in different variables, in different places with different protections. That's easy. If you have setup options that you really care about, store them not in a setup variable, but in the setup something private that has right protections to that. And the rest of the setup settings store in the regular setup accessible to the runtime. Remove runtime access whenever not needed. So some variables do not really need to be modifiable by the OS or even readable by the OS. If you dump the variables, like for example using chipset, you'll see a whole bunch of them, like almost 100 of them on your system from the OS. 99% of those variables are not needed to the OS. The OS doesn't touch it. None of the applications touch it. Why they have runtime attributes? They shouldn't have. They're only needed for the firmware. Make some variables read-only. If OS needs to read them or applications needs to read them but not modify them, make them read-only. There's a variable lock protocol in ADK2 reference implementation that firmware can use. Authenticate variables. There's a whole mechanism defined by the UEFI spec to authenticate variables. Remove debug test content. For example, policies to disable hardware locks that are really useful during the validation pre-production phase, but really shouldn't be there in the production systems. Use PCD settings for some variables. Those are kind of settings that can configure your BIOS during the build, not runtime. Some variables do require physically present user. For example, setup mode in the secure boot implementation. It needs to be only modifiable when user types something or presses a button. Or the firmware implementations may actually implement some integrity checks, as we've seen on some systems on the critical settings. And of course, storing BIOS passwords is probably not the in clear or any other sensitive contents like Wi-Fi passwords or something like that is not a really good protection in the variables. So the other class of common sense recommendation is to validate contents of those variables. Assume that the contents of the variables is malicious or are malicious. Validate them before consuming by the firmware. Is there an address in the variable? If there is an address, make sure that it's not pointing to your own code or data. Validate data written to the variables. Sometimes firmware knows what the set of data, allowed settings that can be written to the variable, can be stored in the variable. So why not validate the actual value written to that variable through the API that this value is within the predefined set of allowed values. Right? Can you boot if this variable is corrupted? If you cannot, have a default in a place which is protected, right? And enter recovery if you notice that the variable contents is corrupted. And of course, if everything fails, our firmware products need to have a catastrophic recovery mechanism. You press the jumper and something happens magically, like restoring all the defaults, including configuration. So one of the way to protect the variables is read-only or variable lock protocol defined by the implemented open source in the reference implementation. So the way it works is there is a variable lock protocol loaded during the Dixie stage, during the firmware, which exposes API, this request to lock that any firmware component may invoke to request that a specific variable will become read-only at some point. So at this point, all the variables are read-writable. But at some point, and that point is end of Dixie, end of specific stage, where firmware almost hands off to the bootloaders. At that point, these variables that were requested to be read-only become read-only and not writable anymore, not creatable, not deletable. And exit boot services, for those of you who looked at the UEFI, exit boot services is the point of handing off to the actual OS. So this is where OS will start, and the OS at that point won't be able to write to those read-only variables. Okay, so that's all for this class of issues in the UEFI-based firmware, and we're jumping to the third class, which we call poisonous pointers, or attacking SMI handlers firmware via invalidated input pointers. And we are biased toward BIOS, so where is no bias for us, there's boredom, and the BIOS actually makes life interesting for us. So with that, I'm switching to Alex to continue with explaining that type of issues.
Hi, my name is Alex, and I will continue this presentation for this type of attack and the next one. And before we start, I want to describe a little bit basics, that we make sure that we're all on the same page. So what is SRAM is? This is protected memory where all SMM code live, including SMI handlers. And this protected range, the pointer to this protected range is live in SM base MSR, which is accessible just in SMM. And this range has protection from CPU is range register protection, SMR mask and SMR base. And also it has DMA protection in the memory controller. If you look a little bit deeper inside SMRAM, there is area name CPU safe state area, which this area is used by the CPU to save and restore context of CPU registers, SM base address. And there is also entry point to SMRAM name SMI default handler or SMI entry point, which live in SM base plus 8000 hex. And I will describe the bug which is related to SMI implementation. So the basic idea is that SMI handler get the input from the argument from OS. So OS pass the argument to the SMI handler through the general purpose registers. And as you can see here, from REcon register, they pass the code for SMI. The RBX, they pass the pointer. In this pointer, in a legitimate way, should live in OS memory. And the RBX, they pass the function number. This is how the legitimate way this work. Why they need actually this piece of memory inside the OS and pointer to them? In a legitimate way, SMI somehow want to return the status of SMI. Is it fail or not? And this memory, they put the status to this memory to the operation system know that this SMI is pass or fail. And what if this pointer will be pointing back to SMM? What happened? And this is the whole thing about this bug. So SMI handler doesn't validate the pointer. So that doesn't check that the pointer pointing outside of SMM mean you can override something inside SMM. How you can exploit this? So what you exactly want to override? In many cases, you don't control the address. You don't control the value which you override. You just can control the address. So you just know where you want to override, but you don't know what you will override. You can pick different options what exactly you want to override. For example, the default handler code, which I mentioned already, the entry point to SMM. So if you can override this, it can be exploitable. You can override internal some structures flag, which related to SMI handlers. And also you can override CPU save state and the field inside the state. And there is one field which is really important, SM base. So this value is pointing to SMRAM. And this save to CPU save state when it comes to SMM, and they restore this value when exit from SMM happen from the resume instruction. So if we override this SM base value, the next SMI which will come, they will come in a new SMRAM and will start execute from malicious code which will be not in protected ranges. I will describe that a little bit more later, but how we know where is SM base is? If you think about this, if you wrote exploit in ring 0 and ring 3, this is the problem really related, really saying that ISLR in a kernel or user space application. So you don't know the context of SRMM. You know the address which you can override, but you don't know where the SM base live, where is exactly this stored. What you can do? You can dump the all context of SRMM in the different ways. You can dump it from another vulnerability, as you already mentioned, a attribute script. You can use this vulnerability to dump entire SRAM. You can use, and in this technique, you will need to use graphic DMA, and I will describe a little bit later more details about this. Also, you can dump all SPI flash, extract all SMM Dixie drivers, and reverse engineer them to find SMM initialization flow. And in that flow, you can find the value of SM base. Also, you can use another SMI pointer vulnerabilities, which is make a memory leak from SMM content. And the last one, if you have debug capabilities, JTAG debugger, you can do this offline and just to make a dump. If you don't have if you cannot find any way to dump the whole entire SRAM, your exploit can try to guess where is SM base is. And there is couple location which is more probable it can be. So it can be SMRR physical base minus 8000 hex, or it can be an SMRR physical base address. Or you can try to override a couple times different pages inside the SMM in a specific offset to try to catch SM base in experimental purpose, and after that use this value to exploit the vulnerability. Here is a little bit description about dumping the SMRAM through a graphic. So basically, we assume that TSEC is not locked, that DMA can have access to the memory, and the TSEC is below SMRAM. And in our specific exploit, we use a 3-boot script to unlock the TSEC, but there is many other options. After the TSEC is below SMRAM, you can configure it graphic paging tables to look inside SMM, and you use graphic aperture to get access to. So basically, all idea is use graphic DMA to get access to SMRAM. And after you have already the address of SM base, you start thinking about how to exploit this. And in a legitimate way, how the SMI work, as I already described, you send SMI and your argument is in general purpose registers, and one of them is pointing to the OS memory. But you assume that you can overwrite SM base and there will be a different location of SM base. In our case, it will be 0 because we overwrite SM base to 0. But before you trigger this vulnerable SMI, you need to prepare the next default SMI handler, because next SMI will use already new SM base value. And in new SM base value, you need to prepare the old stage, minimum stage, to execute SMI entry point and all of this. And in our specific case, we allocate the default handler in address 8000 hex. We allocate our shellcode, which we wanted to execute after we trigger second SMI. So now we trigger first vulnerable SMI, which is overwrite SM base in a new value, which is 0. This allows to next SMI start to execute it from X0, 8000 hex address, and here is already start executing your shellcode, your malicious code in the context of SMM. So code has SMM privileges, which is more privileges that turn 0, and you can do whatever you want. In our specific case, we disable range register protection, flipping the bits inside SMM mask MSR, and we replace SM base for default value. Then all SMM code can execute correctly for the all next SMIs. Here is a demo. So we run the exploit one time. So here we check that SMM is protected and we cannot read it. So the address is all Fs. Then we save the original new SM base memory that we don't corrupt anything. Sorry, I didn't stop the video. Then we prepare the new SM base memory with new SMI default handler, and the trigger first SMI to change the SM base, and the next SMI we start execute from our controlled memory, which is unprotected but with context in SMM, so with more privilege mode. And then we disable the regular SMM protection, range register protection, and then we check that now we can read and write the full SMM, the entire SMM. And if you run this exploit again, this tell you this SMM already doesn't have protection, and you can read and write it directly. So let's back to the slides. I already described this. All of this bug is related to old UEFI-based system, which is used the argument for SMI pointers through the general purpose registers. In the new EDK2 based firmware, the firmware doesn't use the general purpose register for pass the argument to the SMI handler. They use the special buffer to pass all arguments from operation system to SMI handlers. And this buffer named COM buffer, and the pointer to this COM buffer live in ACPI table named UEFI. And this specific particular example, which we can see, this COM buffer is sent the command buffer to set variable, get variable. And the command buffer contain the header, the len, and the status and function ID, and also it's contain the data which the OS want to pass as argument to SMI. So they contain data, GUID, and the name of the UEFI variable. So the SMI handler get this command buffer, and they know that inside this command buffer, depends on this function ID, this argument should be the UEFI variable, and they parse all of these fields. What the problem with this COM buffer? It's really similar to that in the previous class of attack. In this class of attack related to COM buffer, the SMI handler doesn't properly validate command buffer. So you can manipulate from COM buffer to overwrite SMM. And here's example. If you check the line in the bottom with copy mem, you can see the destination address is pointer in the data. And if you follow this data, you figure out that this data is coming from COM buffer. And there is no protections, no checks, and any validations of this data is not pointing to SMRAM. So if attacker already controlled the COM buffer because attacker controlled the pointer in the CPI table and the memory which is in that memory and in this case you can control the data and you can overwrite SMRAM. Okay, I will be fast. So another type of bug is really same the command buffer. There's a stress condition or a double fetch. There's basically a window between check and use the command buffer fields. So you can modify from for example, from graphic DMA this field after the check, but before they use it. So how we can detect and mitigate this kind of bug? There is chipsec module, which can get the parameters configuration file with the config how you want to check. So in this specific example, you point that in SMI 1F, you want the address to the memory will be in RBX, and the all rest registers will be random. So, and here is a detection. It should be video here, or it should be live demo here, but I will continue. Video? Demo? Okay, demo.
Should I continue?
No, just demo.
Sam? So, how much time do we have? 0? Oh. Okay, it was, I thought we had 90 minutes. 60? Oh, come on. Just so much interesting stuff here. All right, well, we'll just have to close up, right? There's another class that we thought we would talk about. It's called One Missed Call, or how we call it. And this is really attacking SMI handlers via the SMM callout vulnerabilities, right? So I'll just scroll through it. If you have a photographical memory, you should be able to see it. But I can tell you that mitigating that specific class of vulnerabilities is like trying to fit an octopus into a pair of tuxedo pants. So, but it is possible. We can do it. And so there's a slide of why we're actually investing in an open source framework tool that detects some of those vulnerabilities. There are multiple reasons to do that. So security researchers need a way to develop POCs, test exploitability and impact of the issues, and also they need to provide that information, to the OEMs and BIOS vendors so that this industry can improve their products. And we also need security researchers to be able to capture that research in a consumable way, right? We also want corporate IT enterprises to be able to actually run it and detect vulnerabilities on their systems that they're about to deploy on to their employees. And we believe that it's got to be an open source so that everyone can see what it's actually testing and which vulnerabilities it's actually testing. So conclusions. The UEFI BIOS firmware security is an industry-wide concern. Everyone is affected or may be affected. And there are often multiple issues of the same time, and some unfortunately take years to mitigate. But researchers keep finding dragons and drive awareness, and also classes of vulnerabilities like those SMI pointers or S3 boot script, they start disappearing, right? And many OEMs and BIOS vendors start to be responsive to the security issues, stepping up to improve security of their products. Even use TripSec, as we know, and even hardware protections are being slowly adopted. So with that, let me just read it because I don't remember I remember the Russian word saying, but not the translated one. So I was told that this road would take me to the ocean of death and turned back halfway. Since then, crooked, roundabout, godforsaken paths stretch out before me. So we'll have to continue that research. There are acknowledgments. I don't have time, but I do acknowledge all the people on this slide, including researchers and people who helped us at Intel, and the UEFI forum members. And with that, we are leaving this scene. Thank you.